nearby is actually light from that same galaxy that has propagated through the universe, and one of them is a picture of that galaxy when it was first born, and the other one is a picture of it in middle age. We can't distinguish that. So it's possible the universe is smaller than we think. Most people are not embracing that idea. But the issue of why is it a problem that the whole universe appears to be at the same temperature, to a few parts per 100,000, is that for objects to come into thermal equilibrium, there has to be a pathway for conduction of heat. So if I take a metal rod and I heat up one end, if it's a piece of copper, almost immediately the other end is hot. If it's a piece of indium, which has very low thermal conductivity, one end can be melting hot, and the other end is just room temperature. There has to be a pathway. And the only pathway we know for heat to convey in the universe, there are no wires, there's light. So in order for the whole universe to come to thermal equilibrium, there would have to be, it would take billions of years for heat, one hot area of the universe, to convey its heat to another area. There just isn't time for the equilibrium to occur. But the theory of inflation explains that problem, or provides a solution. So, yes?
Well, but I don't understand why inflation has to make that separation so fast. You know, in one of the illustrations from lecture 2, you show that all the particles in the universe were very close to one another early on, and
right.
Probably in thermal equilibrium.
Right.
Right. And then they separated, but so something that was 100 degrees here and 100 degrees here, they retain those temperatures.
Right.
For example, but why does it matter how fast they separate?
Because the speed of separation defines the size of the universe today. The theory that you come up with has to be consistent with what we observe. And our observation is that the universe is at least 13.5 billion light years in size.
Yeah.
So to get that big and have thermal equilibrium, those two things together is a challenge. If, for example, if you had different temperatures around the universe and let it, instead of having this behavior where everything is close together and then there's a rapid expansion, instead, if it's more like what Gary said, that is just a gradual expansion, they would have the same temperature initially, but there'd be no chance for the variations that we do observe to get evened out. The only way it works is, the only currently popular theory is this inflation idea that everything was together, and because it was together, it was all at the same temperature, and then the universe expanded at a rate necessary to get to the size that we now observe. There's some tension there between uniformity of temperature and the size of the universe. All right, so let's get into this, because there's plenty to cover here today. We're going to talk about the cosmic microwave background, which is the oldest light that we see from the universe. This is light that was formed and emitted just when the universe became transparent, when the temperature dropped to the point where atoms could form. And light was emitted, and that light, because the universe became transparent, that light can propagate to us, and we see it if we went outside today with the right technology, you can see this. And this is, we'll go into detail about what this picture means. So this is the same drawing I showed in lecture 2, George Gamow. Now, this is, for me, personally interesting because I met one of the characters involved here. So Ralph Alpher, here shown here as a middle-aged man, was an a graduate student at Georgetown University, Cornell, in the late 40s, did a PhD with his supervisor was Gamow, who was sort of an amateur comedian, impish character. And Alpher was, let's go back to this. Alpher was one of the students covered on this page when Gamow said to students, show me proof that all the elements that we see in the universe today were all created in the Big Bang. And Alpher and his fellow students got to work and they realized that can't work. And the reason is there was a deficiency in the number of neutrons. Neutrons are essential to building bigger atoms. So you don't need a neutron to create hydrogen. But as soon as you get to heavier elements, you get all these others except for hydrogen. There's a neutron in the nucleus. And neutrons, we'll go into this in a little more detail, neutrons don't survive. If you have a bottle of them, half of them are gone within 15 minutes. And the early universe just didn't have enough neutrons to create all the atoms that we see on this graph. Alpher was one of the guys working on that problem. And in the process, he produced a PhD on nucleosynthesis in the early universe. And 1948, he published a paper in a professional journal that he was the lead author. Gamow, who had a reputation around the world, he was a Russian emigre and he was highly respected, he thought it would be fun to add Hans Bethe to the list of authors of Alpher's dissertation paper. Now, Hans Bethe had already produced the theory that exists today, even today, on how the sun produces energy, and later won a Nobel Prize. I think 1956, Bethe won the Nobel Prize. But Bethe had an enormously high reputation. So Gamow said, let's have Alpher, Bethe, and Gamow write a paper together. And it was a joke. And the result was really tragic, because everyone who saw the paper said Alpher's on there because of his name. And when in fact, Alpher did the real heavy work of producing a model of the early universe that predicted correctly the production of elements in the early universe, and he predicted the glow of radiation left over from the Big Bang that we now call the cosmic microwave background. Alpher should have won a Nobel Prize, but he was treated as like they included him as a joke. The words here explain that, all this, what I just said. And so we get this first three characters of the Greek alphabet, Alpha, Beta, and Gamma, mimicking the three names. It's a landmark paper in cosmology, but so Alpher was victimized by this. And it turns out that I went to, my aunt got married in the late 70s, went to the wedding. I didn't know anyone from the groom's party, but I sat across the table from Ralph Alpher. I had no idea who he was at the time, but it turns out he is the uncle of one of my very close friends. And I mentioned, hey, I met a guy who's the chief scientist at General Electric. And my friend Alan said, oh, that's my uncle, Ralph Alpher. He's a very bitter man, because he was overlooked repeatedly because of this joke that Gamow played. Right before Ralph Alpher died, he was awarded the National Medal of Science. There was enough noise from the community of astronomers to try to get him some credit. But, and the last few lines of this page address the issue of what's the relationship between faculty members and students, and the issue of fairness. I mean, we know about problems women have with faculty members. Jocelyn Bell, a female graduate student at Cambridge, was the first to detect a pulsar, a special kind of stellar object. And she went to her professor and said, look what I found. And he said, go away, little girl. And she came back with more data, and he shooed her away. And the third time, he said, oh, that's interesting, give me your results. And he and another guy published a paper and won a Nobel Prize. Now the good news is Jocelyn Bell, 2 years ago, was awarded the Breakthrough Prize, which is funded by the Silicon Valley Facebook, Google, Apple, they have this major prize they give out. Actually, the team that makes the selections is in Boulder. And Jocelyn Bell won the Breakthrough Prize in 2018, a $5 million award, I think, which she donated to the community of women scientists in England. She said, I have enough awards. She became famous in spite of being suppressed by her professor. So anyway, it's not all party and good news in the world of astronomy. So this is a page, we don't have to dwell on it too much, but this is a page from the paper written by Ralph Alpher and his colleague Herman, predicting a background glow from the Big Bang at 5 Kelvin. I mean, this is 1948, so there's a lot of uncertainty about how the universe expanded. Here's a modern picture of what we think was going on. That at the instant of the Big Bang, the temperature was 10 to the 32 Kelvin. That is a 1 with 32 zeros. It was extremely warm. And that's at 10 to the minus 45 seconds. So impossibly tiny fraction right after the Big Bang. And then we see this drop in the temperature as the universe expanded over time. The temperature plummeted, and it gets to 600 Kelvin, which is mentioned in Alpher's paper in the pink area, gets to 600 Kelvin right at 380,000 years. So he actually put his finger right on all the essential information in 1948. But there was no evidence, there was no measured evidence. This was sort of speculation. This is more detail, we don't have to go into it. It actually adds, you can look at this in your own time, but it adds some highlights of what goes on 1 minute, 1 year, and so forth, and what kind of things were going on, stars forming, galaxies forming, and so forth. We've looked at this many times. And what we're talking about is, in the early universe, this is the period prior to 380,000 years, just total mayhem. Even electrons didn't exist, just shrapnel. Things cooled, and now we have this recombination interval at 380,000 years. Total darkness until about, this says 300 million, I say 400 million, doesn't matter, and the first stars appear because of gravity. Oh, and we should fill in a little gap here. I mentioned earlier that gravity formed galaxies. Gravity also formed the stars. So if you have clouds of gas, this hydrogen gas floating around, there's gravity there too. Two hydrogen atoms are attracted, and eventually clusters of them get together where there's a little more hydrogen here than over there. This becomes a center of collection. Gravity draws that stuff together, and if you have a big cloud, it gets dense enough, you get a star. Yes, sir?
I thought somewhere it said that Einstein said that gravity isn't a force, it's a curvature of space.
Right.
So we
Absolutely.
keep talking about it as a force.
Mm-hmm. So the easiest way to introduce gravity and discuss it is based on our personal experience. If I take anything and let go, it will accelerate downward till it hits the floor because there's a big planet here. It takes, to show you how weak gravity is, it takes a planet the size of Earth to make a pen fall at some acceleration. Einstein, and that's all based on Newton's theory of gravity, which works great. When we go to Mars, use a spacecraft, go to Mars and so forth, or Pluto, it's all done using Newton's law of gravity. It's simple. And I could write it on the board now and explain it. It just takes a few seconds. Einstein came along 200 years later and said, that's not really what's happening. But Newton's expression for gravitation works fine in everyday life and exploration of the solar system. if you want to get into what's going on the scale of the universe and why strange objects like black holes exist, then we have to embrace Einstein. So there's a few charts in a row to try to hammer home what we know about the early universe, including this. And this is the first detail we're adding to how the universe, when it became transparent, what happened. Remember, the universe was much smaller then and much denser. And sound waves can propagate in, as long as you're not dealing with a vacuum, sound can propagate. Sound is propagating in this room now because it's filled with mostly nitrogen and some oxygen. And we'll go into this in more detail, but it turns out in the early universe, when the universe became transparent and the cosmic microwave background was free to flow eventually to find its way to us, there was sound in the early universe. And we're going to hear what that sounds like near the end of this presentation. Pam, I'm going to ask Pam to make sure we have a break at the appropriate time. Thank you. So, I mentioned Alpher's work, 1948. He and Herman and Gamow wrote a paper. Most people didn't worry about it. In fact, at that time, the study of cosmology was in the doldrums. There were not, if you were a student and you went to a professor and said, in 1950 and said, I would like to do a PhD on cosmology, they'd say, why don't you just get a music degree? Because you're never going to be a scientist. 64, everything changed. In New Jersey, this machine, which is kind of like the size of a suburban house, was being built to develop technology for long-distance telephone calls by Bell Telephone Laboratories. And all of us are of an age when we remember when Bell ruled the communication world. And they had vast resources to do research. And microwave radiation, or microwave communication, looked like a good way to send a signal over long distances without having to run wires, which is expensive. So they have radio scientists building and experimenting with antennas of this type. Actually, you can see roughly the size of this. There's a door. This is the control box, and there's a door. And this thing can rotate, see, it's kind of like a wheel assembly. This thing can rotate around. And experiments were being done by these two guys, Penzias and Wilson. There they are standing next to the antenna. And they could rotate the, so this is like a sugar scoop. So it has an opening that you cannot see in this photograph that points at the sky. And because it has this wheel assembly, they can rotate that. And wherever they rotated it, it means the antenna is collecting information from whatever is out there. And no matter where they pointed it, they kept hearing zzzz. And they tried everything to figure out what this was coming from. They used low temperature devices to quiet the noise in their sensors, which were vacuum tubes. That's tricky, you know, cooling down a thing that has a hot source in it. They tried everything. They could not get rid of this buzzing. Then they had an inspiration. Pigeons. Pigeons are nesting in the thing and leaving guano in there. So some poor technician at the Bell Labs had to crawl in there and clean the pigeon poo out. It didn't help. No matter where they pointed, they heard this buzzing noise. And it was at around 3 Kelvin. I'll show you what that means when you listen to a radio signal and say it has a temperature. We'll talk about that. Not far away, this guy, Robert Dickey, was a professor at Princeton University. And he had a group that was the tiny little nugget of what now is a large field of cosmology. Dickey was interested in everything. And he had gathered a bunch of smart young professors and graduate students, and they were interested in everything. And one of the things they were interested in was the early universe they kind of knew about what Gamow and Alpher had done, but this is sort of the beginning of the real science of cosmology. And they wrote, Dickey wrote this letter, it's got a little note here saying, hey, the guys, Penzias and Wilson at Bell Telephone, they're seeing a signal at 3.5 Kelvin. Where's that coming from? And here's a map. This is how science happens. Here's a map. On the right side is Holmdel, New Jersey. That's where the antenna was. And on the left side is Princeton University, and it's like 57 miles, 51 miles. And one day, a colleague of Penzias and Wilson went to Princeton and attended a seminar, just talk about things, and went to Dickey's seminar, and finally the link was made, well, yeah, we're making measurements of that thing you guys are thinking about, of what is left over from what created the universe. At this time, the idea of a Big Bang was, for a large part of the astronomical community, a joke. In fact, the term Big Bang was created as a pejorative. What's wrong with you people? You believe there was a Big Bang. And its name has stuck, just like black hole was an issue too. We'll talk about that. So, what were the Penzias and Wilson measuring? Yes, sir.
You met Alpha. I met Arnold Penzias. I went to high school with him, and he signed my high school yearbook.
What? Holy. Did you get any of the Nobel Prize money?
No.
So Penzias and Wilson actually got a Nobel Prize. You know, this is an important thing to understand. They were the first to detect the cosmic microwave background, and by a few accidents of the fact that they were in New Jersey and Princeton is in New Jersey, and some friendships existed there, people started making connections between measurement and theory. But Penzias and Wilson didn't just make measurements. Once they saw this background and understood its possible significance, they really drilled down on it, and they made a scientific study, as I will show you. I'll show you what they did to measure the temperature of this globe in the sky. So, we have this drawing here. This page is intended to show you two things. First of all, if we look at the distribution of temperatures of Earth, we've all seen these pictures, these so-called heat diagrams, and you see the mid-latitudes are warmer and the poles are colder, and there's a scale that shows us how the colors are coded to tell us what the temperature is over the distribution of the globe. This is a Mercator projection. This is a picture, a distorted picture, but a picture nonetheless, of the entire globe in one picture. So it's as if we take a globe that you might have at home or in a school classroom, and cut it up and lay it flat and then stretch it so that it forms this oval. So there are two messages here. One, heat maps can be useful. And second, this shape is important, and the cosmic microwave background is always shown using what it looks like a Mercator projection. If we pick a spot, let's say any spot on the sky, and we call that north, right here, the opposite direction is south. And then as we scan around the sky, we begin filling in this drawing, and this point and this point are the same point. Just like if you look at that globe, this Mercator projection, this is a spot in the Pacific Ocean, that point, and that point is the same spot. So if you travel eastward on here, you reappear over here and so forth. This drawing is showing the same thing, and it shows the distribution of temperature on the sky measured originally by Penzias and Wilson. And notice the temperature range here. Here, the temperature ranges from -63 centigrade to 37 centigrade, so about 100 centigrade. Centigrade degrees and kelvins, the scientific degree, are the same interval. Now, let's take a look at the range of temperatures, the hottest and coldest points here. This goes from -270.42 5 to, that's the